Greetings and welcome back. So we're getting close to the end of the course, and I will have a number of sort of opinion pieces, so to speak, that came up in the context of things we've talked about this term. And one that I feel is very important is this question of whether we need to study the real biology to learn the so-called real biology. And I'll elaborate on that in a moment, but it has to do with the sort of a progression of realism, I suppose, is what you could say. And what I've noticed over the years is that there's a certain kind of harshness that comes in the process of refereeing, where somebody that works on something that's closer to the so-called real system will look down their noses at somebody that works on something that's so-called more artificial. And you could use the entirety of biochemistry as the sort of victim of this kind of thinking by arguing, well, that's not the real biology. But even a very interesting point that you can observe in biological discourse is even the use of the word in vivo. And for example, whether or not somebody that's doing some cell biology, even whether that's considered in vivo or not. And so, anyway, I want to. This will be a short vignette, but it will, I hope, be potent. So let me begin actually in a different context, which has to do with the study of atoms. And so I think that more or less anybody that would be inclined to listen to this course and have listened for this long will have surely encountered the idea of atomic physics, or the ideas of atomic physics, and the idea of energy spectra and that sort of thing. They will have heard of s, p, and d orbitals. And if they're a little bit more sophisticated, then they will have learned a little bit about ideas like the Schrödinger wave equation, which is the way that we characterize the properties of waves, the wave function in atoms, for example. And what I wanted to say is that there's a progression of models that one learns at the beginning of one's first acquaintance with quantum mechanics. And one of the favored examples is the so-called particle in a box. And I indeed remember the first time I learned about the particle in a box feeling how it seemed highly contrived. It was like, really consider a one-dimensional rectangular, a one-dimensional line of an atom that's in an infinite potential. And that seemed incredibly contrived. And I guess the thing I want to say, which I find remarkable, is that over time, as people became they used more and more ingenuity. The group of Don Eigler at IBM was able to use the STM to, as you see on the left, to arrange a series of iron atoms, I think, if I remember correctly, in a circle. And then using the STM, they can measure the wave function of electrons that are found inside of that circle. And this is something that I offer as a homework often, that I think it's a really fun homework problem to, it's almost like a rite of passage to work through this problem and to try to understand the wave function for a highly contrived, artificial, in this case, two-dimensional circular infinite wells at the edges. And so it's shown on the right as the energy levels. And, this is giving you a perspective on a progression of what I would call school child exercises, being a little bit obnoxious there because obviously this is deep and sophisticated. But, you learn about the harmonic oscillator, you learn about the infinite square well, which is what I just told you about. Then we learn about things like the finite square well. And then, you can put in various bells and whistles. And as one does so, the actual precise nature of the energy levels changes because the model is a little bit different from one case to the next. But all of them share, just for example, in the insight that the energy levels go like h bar squared over 2ma squared, where a is a characteristic length scale. There will be some correction factor. But my point is that who would have thought at the inception of the particle in a box that somebody would be clever enough to come along and be able to make the particle in the box at the level of atoms. But also, the thing I'm showing in this particular diagram is that we learn a lot by looking at the contrived example of the particle in a box. In fact, I would go so far as to say that, and I think this is true in some quantum mechanics classes, that a lot of effort's put on models that are not the actual atoms that people might care about, and yet people will still have an insight into the behavior of atoms as a result of that. Now, let me turn to biology. So I've heard, the reason I'm inspired to give this talk or this vignette is both personally I'm inspired because of my interactions with both reviewers, but even more importantly in the form of conversation with colleagues and friends, and even more significantly, I think, in watching sort of just the exchange that I see take place between different scientists that I know. And I'm being critical right now. I think that people lack generosity when they give this argument that this or that thing is not the so-called real biology. So, one of the most inspiring experiments that I ever learned about, and actually led in many ways to me getting in touch with Julie Theriault, and she and I working for the last 20 years practically on a book together. We're on the third edition of a book that we've been doing together, and I was super inspired by her work on Listeria. So this is a bacterium that hijacks the host cell cytoskeletal actin machinery in order to propel itself around within the host. And in the top series of images, what you see is this characteristic comet tail, in which the bacterium basically inspires and creates the actin polymerization in its wake, which actually pushes it along. And the thing that kind of blew my mind is the thing in the lower right, which is the use of a coated bead. I think it was coated with ACT-A, if I remember, which is a particular protein. And this behavior was reconstituted on, an inanimate bead, a 1 micron-ish sized bead. And, we can get into conversations about what is learned and how we each define understanding, but it starts to feel a bit like splitting hairs to critique this kind of work and say, well, that's not the real biology. I would say, here's my summary statement, a admittedly subjective statement, but one strongly held, which is, answer me this: is the world of science better off because somebody did the experiment with the coated bead, or is science worse off? And man, I would like that debate with somebody that wants to tell me that science is worse off because of such artificial experiments, which are not considering the so-called real biology. So that's example number one. A second example, also involving the cytoskeleton. This one I think comes from Marlene Dogterom. She may have actually been collaborating with Julie Theriault on this one. I don't really remember, but here the idea is, one is interested in the mechanics of cytoskeletal filaments and their ability to do work when they push on a barrier. And so here they held on to an axoneme, a bundle of microtubules, and then allowed one microtubule to grow into this barrier, and then watch the relationship between force and growth and catastrophes and so on. And the details of that are irrelevant for what I want to say. A corresponding experiment from Dan Fletcher that I truly love, it's, again, I'm telling you, like the Hall of Fame experiments for me. This one has to do with using a cantilever and letting a meshed actin network grow from below and push up the cantilever. That allows you to measure the force extension properties of this collective of actin. And the fluorescence allows you to tell you also how many there are. And so you've got basically a force velocity relationship. The reason you know the force is because the degree of deflection of the cantilever, using the beam theory that I talked about in some weeks ago, you can work out what the force is. So all three of these are, in my opinion, really potent examples of not looking at the real biology and yet being enlightened. And again, my simple statement is, do people that make these arguments, do they really want me to believe that their view is that science is better off without these so-called artificial examples? If so, we have much less in common than I would have thought. It's a matter of beauty. It's a matter of curiosity. It's a matter of controlling the knobs carefully so that one can make a rigorous measurement. And so it's just a little beyond me that one would critique this. So another example that we already did that I think is really fun from the sort of developmental biology perspective was this idea of tuning the dosage of Bicoid and thus changing the quantitative character of the positional information in the sense of Wolpert and the French flag model that we looked at earlier. And, that led to this extremely interesting prediction where we predicted how a morphogenetic feature would move as the Bico gene dosage was changed. And the curve, the line, is the result of that prediction. But the data is the data, and they don't correspond with each other. And again, we can take cheap shots and say, well, obviously such a simple model wouldn't work. But that's not, to my mind, that is not the route to progress, is to just diss things and say, well, I knew ahead of time. No, you did not. You did not. Nobody knows ahead of time. That's why we do experiments, because sometimes we didn't know ahead of time. And I keep on referring to Lamarck, and I will continue to refer to Lamarck because Lamarck is a hero to me. And the fact that he had a wrong hypothesis required people to do experiments. And there was even experiments, if I remember correctly, where people were removing the tails from mice and seeing whether that would be inherited. And bottom line is that these artificial things can be useful. Now, in the laboratory of Steve Small at NYU, he had the idea, continuing to riff on this positional information idea of flattening the gradients out and then looking at the resulting phenotypes. And here I'm not going to, you'll have to look up Steve Small's work. I think this is in a paper in PNAS, if I can remember correctly. I'm sorry for not putting the citation, that was careless. But I'm racing to keep ahead of the class. And that means that I've fallen short, as I mentioned earlier in my critique on my use of the literature at the beginning of the term. So what he did is flattened out the gradient and then tried to look at the resulting structures, developmental structures that arose. Another example of a very beautiful experiment. And I just wanted to report from just in the last couple of years, this really takes it to the limit. I mean, take a look at this. So it says, to explore what features are sufficient for positional encoding, we asked whether arbitrary molecules, e.g. green fluorescent protein or mCherry, could be converted into synthetic morphogens. How wild is that? And this paper also pursues that same theme, patterning growth control in vivo by an engineered GFP gradient. So, this was in the context of the wing of the fly, but, it shows you, okay, so what? Is this a parlor trick, or is this profound? And I think what I want to say is that because of the exquisite control, they're able to control what the morphogen is and then how much it's expressed, and they can watch it to boot. It's like you design this experiment so that the thing that you use to measure the system is the thing that controls the system. So in some sense, the GFP is no longer a perturbation, if you want to think of it that way. Often, I like to joke around that, that when a protein is fused to GFP, it's basically, I want you to imagine, linked arm in arm with somebody else and living your life all the time, 24/7 with that person, that size, somebody your own size walking around with you everywhere. And so at any rate, that was the point I wanted to make, is that is this idea that, what we call the real biology, I think is a red herring. It's a way to inhibit the conversation, I think, about how to know more about the world. That's what I think we do when we make such critical remarks.